All right, physics reaction video number 63. This time I did a search for high school physics filtered by this week. And so I think this is something fresh and new. Apparently this is chapter 7, number 16. I have no idea what that is. It says physics 102. So maybe a college course? We'll see.
Okay, 102 students, I got a good question here about chapter 7, number 16. And it is really relied or going back to the definition of work. And this question is trying to address a fundamental concept of work that's a little bit hard to, what's the word I'm looking for? To accept. I guess you might say it's a nitpicky rule. But because it leads to the principle of conservation of energy, it's important that it be nitpicky, okay? So when we say work is force times distance, we clarify that by saying it is the amount of force in the direction of the distance. Cool. So maybe I should just put here amount of force in the same as the
So it's interesting, right, when you think about the compactness of modern mathematical notation. So the dot product with little arrows over these, or maybe these are bold, means all of this, right? Hey, you, how much of you is parallel to me? That's what I have my students always say. Can you guess what I have them say for the cross product? Hey, you, how much of you is perpendicular to me? So it's the compactness of the notation carries just a ton of information. I actually really like the fact that he just wrote this out. I am going to guess that they haven't actually seen the dot product notation, just based on sort of what he's doing here. But this is, a tricky thing that students have to deal with. And so far, I really like what he's up to. A couple of comments. Great framing. It's amazing. It almost perfectly matches his legal pad. Did you notice there was a little bit of the autofocus problem, but not when his hand is there. It's almost like when he shrugged or something. I'm guessing this is cell phone vertical video syndrome here, and which means the microphone is probably right about where his mouth is. So it's actually really great logistics to get really good sound. The red is I was expecting black. I wonder if black would read better, but the red is nice. Although red scares students. We're told not to use red pens to grade. So looking good. And I've actually switched back to using lined paper. Well, I use my phone and a stylus, but I actually add lines. It actually helps me stay neater. I used to always just do blank paper, and I'm not, I think it's a wasteful use of space if you don't have the guides like that.
D. So there's not really an issue if, say, the force is to the right and the D is to the right. You just take, the number, say the force is 4, and you multiply a distance, say, of 3, and you just multiply them together by 12 and get 12. And the units, of course, for force are newtons, and the unit for distance is meters. That is given in the honor to joule, and so you get 12 joules. Okay, so that's the easy case, and maybe even a case that you saw in middle school or high school.
So I'm guessing
it gets a little bit harder, though, when you have something that is like this. What if the force is straight up, call it 4 newtons straight up, but the movement is horizontal at 3 meters. Well, in that case, and this is why we've kind of been trying to learn about our vectors, we even did a lab on vectors, we've got to say, well, how much of the 4 is in the direction of the 3? So it wouldn't be the full 4. So you wouldn't just go 4 times 3 like we did back here. And in this case, if the force is purely up, then none of it is horizontal. So when you say force times distance, you would have to put a 0 force, because that's the amount of force that's in the direction of the 3 meters. And 0 times 3 is 0.
So I'm just going to pause there, right? Because there's two ways he could have done that, right? He could have said, hey, how much of the force is in the direction of travel, which is what he did. So we put a 0 here. Now, of course, he can also say how much of the travel is in the direction of the force. So then you'd put a 0 here. And in fact, you can always do it that way, right? So I guess my question for you guys is one of those two more proper, right? Is it one of those two more clear sort of description of what's going on? I think that if you're talking about kinetic energy, like work causing kinetic energy, I feel like, it's interesting because kinetic energy is a scalar product, so it doesn't have a preferred direction. But I think most of you would say the way that he did it here, that, find out how much the component of the force that's in the direction of travel and use that. But I kind of feel like you could say it the other way and be consistent with that. And of course, you get the same answer. So I'm intrigued by that. I'd love to hear your thoughts about that.
And of course, I guess it would still be newtons times meters, so 0 joules. Now, if the force was kind of at an angle, let's say, so we've got 4 newtons, and then we move horizontally 3 meters, well, then there is some.
Just want to pause here and ask whether people think that this is an issue, right? So forget about the units for a second. This vector is shorter than this vector. So how can this be 4 and this be 3, right? So if the units of the vectors are different, can you draw them on the same graph? I do this kind of thing all the time. Though I think it's interesting. I would normally label this as F and label this as, I don't know, X or D or something, and then come over here and start to put some numbers down. So I wonder if putting the numbers next to the vectors might make a student or you think, wait a minute, how can this be shorter than that? Well, they're different units. So to say is one bigger than the other actually doesn't make any sense, right? You can only ask those questions if the two things have the same units. So it seems like this is easy to clear up if a student were to have that problem, but I just wonder about that sort of gut reaction, like how in the world can 4 be less than 3? I'm going to turn off now, right? How much of an issue is that? So it caught my eye, but I'm already loving what he's doing, right? He's dropping the perpendicular. I'll just point out that you could have also dropped the perpendicular this way, right? To do, to break, let's see, how do I want to say it? Drop the perpendicular this way. Yeah, you would break this vector as a little bit this way and a little bit this way. And remarkably, you get the same answer.
Force. Well, let's say it's angled enough so that that's equivalent to being 2. Well, then, of course, when we say force times distance, what we mean is a force amount of 2. So it's not the whole force. It's a fancy word is the component of the force. It's the amount of force that's in the direction that it moves.
Cool.
So in this case,
what I really like that is he didn't bother with cosines and sines and figuring out a perfect 3, 4, 5 right triangle or anything like that. He just put a number down. Now, he had to put a number that was less than 4. But that's it. That's all he had to do, unless he was really trying to match the exact angle he happened to have drawn. As long as he used a number that was less than 2, he's driving his point home. And for the moment, he's skipping the notion of how do you calculate that using trigonometry or whatever. And so I actually think that was really, really interesting.
a 2 times a 3 would be a 6, and a newton times a meter would be a joule. So even though these 3 examples I'm trying to illustrate each have the magnitude of the force the same and the distance the same, the angle between them is different. And so we have this nitpicky definition, like I said, is real important. Otherwise, you wouldn't have conservation of energy. But this nitpicky definition results us to think about how much of the force. Okay, so with that said, that's why number 16 is here as a conceptual problem and trying to get you to think.
So that was actually really interesting, right? So he actually went 4 minutes and 7 seconds before really talking about the problem itself. So he started, the top of the page said, chapter 7, number 16. And then I actually kind of thought he was just jumping right into the problem. But in fact, this was just support material for the problem. Now, of course, his students have already read it. So we the audience are like, not sure what it is. We can guess what's going to come from this problem. But I really liked the support mechanism. I guess I'm just curious about comparing and contrasting this approach to, ooh, let's set up the problem and then scratch our heads and say, wait a minute, this is weird, and then go do the sort of way of thinking about it. Boy, I can see arguments for both ways. What I like about what he's doing here is he's able to pick whatever numbers he wants. He doesn't have to dive into what this is actually asking, because very likely this is going to have a very particular angle. Here he was able to talk about it with multiple angles and really drive it home. Whereas if you set up the problem, the students are going to be fixated on whatever angle it says in there, rather than being able to talk about it in general up here.
Because it's not a matter of how tired you are, and it's not really what your muscles are doing. Sally's going to be tired because her muscles are doing a lot more work than
problems.
Bill, and I get that. And I think that's what makes this problem harder, is you're thinking of yourself doing the work, and you're thinking about how you're going to be tired.
I hate these problems.
And so Sally and Bill.
When it comes to muscles.
See, this is not really what this question is about. This question is about how much work is done on the bag of flour. and it turns out to be the same amount. See, here it says, Bill's job is to lift the bags of flour and place them in the back of a truck, which is parked right next to him. So Bill applies a force probably roughly equal to the weight of the bag of flour.
Ooh, that was interesting.
And lifts it up a distance of, whatever the typical height of a truck is.
Did you hear that subtle thing, right? He's like, probably equal to the weight, right? So these problems really get you into trouble if you just have, if they don't bother to give you the upward force. You just have to make this assumption, oh, well, they're just lifting it. Are they accelerating it, right? Like, are they lifting it and making it go faster and faster? So this idea of just very, very carefully matching gravity, and maybe just by overcoming gravity by a tiny little bit, it's a subtle thing, but he just he said it so that it's sort of implanted in the brain. I really liked that. Again, now here he just has labels, but boy, I guess I've never really thought about the fact that so often people get fixated on the length of the arrows, and again, they're not comparable. They don't have the same units, but this is exactly what I do. I just put in the labels. So, I'll have to think about that. Like, do we have to worry about students comparing lengths of vectors when they are not comparable?
I'll call it a meter plus. And those are in the same directions. And so this is like scenario number one. And you go, okay, so you just multiply them together. It's the amount of force, which is equal. I shouldn't use a W. That might look like work. Let me just call it mg. And so you would just say mg is the force and the distance is d. And so that would be the amount of work we might contribute to Bill. Okay. Now, Sally admittedly has a harder job here. She's got to lift it up roughly, presumably, about the weight of the bag of flour. Maybe she just kind of lifts it up to the height of the truck at first. Then she carries it across the floor, presumably still lifting up though. Just hold the weight of the bag of flour. Now, maybe she gives a small little tug to get it to start to head in a horizontal direction.
That's interesting.
But she kind of gets that tug back, if you will, as she has to slow it down and she set it in the back of the truck.
Oh, that's interesting.
Those two kind of balance, or you can say they're minor compared to this part of it. But here's the point. Let me call this D1 and T2. She's got two different movements, but while she is moving the bag horizontally, this D2 with her force up, there's no work being done. Again, from this strict definition. And I should say there's no work being done on the bag of flour. That's not to say that her muscles of her legs don't contract and move across. So every step, there is a force and a distance in the direction she is moving. And so every step, her body is getting tired. The muscles are doing work on her body. So again, this is where I want to be a little careful, and it's kind of hard any physics problem to then associate with the human body, and so I appreciate this problem because what they're trying to illustrate is something very important. It's the amount of force and the direction it moves. But it can also be very confusing for students. So I just want to keep saying that this question is asking for the work done on the bag of flour, not the work done so much by Sally, if you will. Or maybe it is. It's just kind of a question that's getting you to think about it. So if Sally is talking about how much work her body has to do, she's going to be tired and she deserves to be paid more. But on the other hand, if you're talking about how much work was actually done on the product, on the flour itself, the answer is the same because this part of her movement doesn't contribute any work, and that's really the goal of this. So I'm not so sure
So, man, I've commented about this before that the word work, getting tired, right, really complicates these problems. He's being honest that it kind of depends what's exactly being asked here. The microscopic issue about why a muscle gets tired when you hold something, the physics definition, the macro physics definition of work, nothing's happening, so you shouldn't get tired. What's wrong with you? It's really, really subtle. So I'm always looking for better ways to do that. So please, in the comments, if you want to, let me know how you approach that. But I just want to go back to talk about how, he was so careful up here, and that not using the dot product and using narrative instead, really talking about multiple angles. And in fact, down here, just used two of the angles that he talked about. I wasn't sure what angles were going to be used down here in 16, but lots of really, really interesting things. And I guess I'll just reiterate that, you can ask this question the other way. You could have put a 0 here, which is like putting the perpendicular down this way. And I'm just curious if anybody does that and if they have strong feelings about it. All right, everybody. I hope you have a great day. And remember, physics teachers are awesome.